right.
So our next presenter is Christopher Pfutzner. He says we can call him CJ. He's a mechanical engineer in the combustion dynamics and modeling section in the Navy Technology Center at NRL. He's worked in a technical capacity with oil and gas blending in Houston, Texas, in addition to serving both the refrigeration and automotive industries since 2009. He joined the NRL in 2017 and serves in various design and test engineering roles. And what he's going to be talking to us about today is viable bench scale experiments of the in-situ burning of California crude oils. Yeah, are we interested in that? Yeah, we are. Go for it, CJ.
All right, my screen should be up. Holler at me if it isn't. Thank you very much, Steve, for that discussion on the burner. That's a fun project. And here I'm going to talk about some smaller bench scale ISB experiments, specifically with California crude oils. I'd like to go ahead and thank all of y'all here at the OSPR workshop and my co-investigators and BSEE for their funding on this. And we're going to talk specifically with some experiments regarding the ignitability of the crude oils in situ. So as we've already talked about a lot today, this is in scenarios where we have crude oil on water and we want to burn it off the water directly. And what we're talking about here is seawater conditions. We're going to talk about the methods of actually prepping the oil. So that includes the weathering of it. In other words, how the time and weather outside affects the oil over time, and then the emulsification process as oil sits with the water and actually becomes mixed with the water. And then we'll go into the results with specifically looking at ignition, time to ignition, the energy required, and the burn efficiency. So how well it ignites and how well it actually burns. I'll put up some contact info at the end. So in addition to questions today, y'all can feel free to reach out to me later as well. And so we're going to be working with 5 crude oils here, all of which are from the Santa Barbara channel. So some of y'all might be familiar and heard the names of Carpinteria, Montargueyo, Santa Clara, Santa Ynez, Sockeye. This is all a range between 33 and 16 degrees API. We'll talk about the environmental conditions, but all this is geared towards the Santa Barbara channel again. We looked at data, August data over 3 years, averaged that, and kind of use that as our baseline. And we'll talk about the weathering, how the oil degrades over time in that environment, and the emulsion regarding the oil and the seawater mixing together. And some of you may recognize these names. On the left, we have the production units again, and running through the densities and the viscosity. So you'll notice we have some pretty decent range here. So including some very, very viscous, very, pretty darn heavy, or at least medium heavy crudes. And all of these are fresh off the pipeline. We have the platforms that they came from on the far right. Some of y'all may be aware that some of these platforms either, are never going to produce again, but these methods that we're going to discuss are just as applicable to any oils. And the environments that we're actually dealing with, that can also be changed with the method, of course. But what we're going to talk about is looking at a water temperature of about 20 degrees C. We're using our artificial seawater. So this is ASTM D1141 seawater. We're going to weather all this for a simulated 48 hours at sea. And so that's necessary to say simulated, because what we actually had to do was model that beforehand, look and see what it actually looks like in terms of mass loss, because the mass degrades differently for different oils. And then we basically run that for 5-gallon batches, run it with 100 RPM, so pretty slow propeller, and weather that oil down until it reaches the mass loss that would be the same as if it had been sitting at sea for 48 hours. And then emulsifying it is a fairly straightforward process. in terms of putting water and oil together and then mixing it with a high shear mixer. The problem is determining, and I'm sure that those in the research area have heard that there's issues with determining what emulsification actually is in terms of stability. And so we looked at stability as 2 hour or greater stability. So that means that it could hold its emulsion for about 2 hours or so before we actually ran the test. Some of these did break down overnight. So we're not going to say that these are completely stable emulsions, but that they're entrained or mesostable might be the literature term for them. But we ran them from no water at all, or no, that would be neat, up to 20, 40, and 60% seawater added to those. And we'll look at kind of the conditions that we actually ran here. On the left, we have kind of the nomenclature. N stands for neat. There's no weathering happening to it. There's no water added to it. So this is just what it comes in a drum and how it burns. And then we have what happens if you emulsify with 40%. So that's still fresh, but emulsified with 40. So we call that our E40. Then we have the weathered neat. So again, no water, but this time it's that simulated weathering for 48 hours. And then from there on out, we have the same weathering amount, but just more and more water added to that. So it's 20, 40, and 60% seawater. And now you might be aware that in certain conditions, there's evidence of more than 60% seawater in an emulsion. But as you'll see later, regarding our ignition tests, this was kind of the most useful benchmark, and also made the most sense regarding time. And we here love a good thermal balance, and so we like to talk about everything in terms of Q's and M's, but I'd like to go through this real quick because this is kind of how we base our experiments and our methods off of. So basically, we have combustion on the surface, we have crude oil, and here it's simplified, but you can certainly know that the crude oil and the seawater do mix underneath. We have the seawater at the bottom, and that takes most of the heat from the combustion on the top. And when you add an accelerant, that might be your combustion at first, and that causes the crude oil to vaporize, and that's that M leaving. As that M leaves, it promotes more combustion, etc. Eventually, that crude oil layer gets thin enough that the seawater takes all of the heat, and then we actually end up with an extinction of the burn. And so we try to replicate that with a small bench scale setup, and so that looks like this in terms of our oil slick on top and our 19C chilled water on the bottom. And so you'll note that this could fit in the palm of your hand. This isn't huge. It is really quite small, and we run water through this. So a lot of what's out there in terms of the research involves putting oil directly on top of water, or if you separate it, not having it run continuously, so you end up just heating up the water over time. So this is constantly chilled with a NestLab chiller down to 19C. And so we're trying to keep that environment stable. It's all made out of stainless steel, so it's pretty darn conductive. The oil does sit on top. This also makes mass measurements a little easier because you don't have to worry about, oh, well, did the water disappear to the bottom? Where did it go? We know, oh, it really did burn up, or it didn't. The oil slick sits on top, and then the water sits on the bottom. And then, of course, if you remember that picture from before, though, we actually need that combustion. So we have a heater on top. And we use the SFPE definition of how to calculate the power off of a 1 meter square pool fire and add that heat. So it's 15 kilowatts per square meter power coming off of this heater. Again, it's not a huge heater, but it's a lot of power coming down. And so that mimics the combustion if you have a fire that's already started, for instance, or you have a little bit of gelled diesel that has been ignited. And then you'll note that we basically put that sample on that sample holder, and from there we run that test as in terms of how long it takes to ignite. So it sits there until it ignites, and then we call that our time to ignition. And we can measure mass. We do actually have shutters. You see a little asterisk kind of right in the center of the screen there, and that's our way of shutting the heat on and off instantaneously so that as we put the sample holder in, which takes all of 10 seconds, that we're not just burning ourselves in the process. And a test involves placing the sample in that holder, waiting for it to ignite, and then once we actually have ignition, we can watch it. So this is kind of what it looks like. Again, you can see that container in the middle, sitting on the sample holder, the flame's going. This is a kind of nice structured flame, which means that this one actually was a neat burn. It's nothing too crazy, not all over the place. It's an easy kind of test to do, and it's certainly way cleaner than dumping oil into the channel and burning it off of there. You'll note that we have these two valves on the sides, and that's the water running through. So that's our chilled water. And we actually measure our mass initial, so that's pretty straightforward, just measuring how much mass we have in the get-go and how much mass we have at the end. Later, we actually got a scale that we can measure the instantaneous mass. So we have that to compare the average versus the instantaneous. We also did measure the heat released, and that's something we can talk about a little bit, but we're not going to go too much into that because there's a lot of, one thing, there's a lot of noise in that data, and we just need a lot more sample sizes. What we ran was 3 times per test at least. So that gave us a good amount of idea of where our margin of error was, but as with everything, it's always nice to have more trials. So that's something we can talk about for future stuff. But right now we'll talk about that time to ignition, or T ignition. And there's 2 ways to look at this. One is literally just the time it takes. So that's just, if it takes 15 seconds to ignite, that's not too bad. If it takes 15 minutes, that's really probably not gonna fly. The other way is to look at the energy. And so that's basically taking that time to ignition over that area that we have. So again, it's basically just the palm of your hand and then that power coming down. And we can get an actual energy out of that. And that's a useful metric. It's useful to compare with some literature values. For instance, it's worth noting that the energy is a useful metric, but the power does actually matter. In other words, the energy over time does matter. So you could have a little bit of heat over a long time, and that'd be a lot of energy, or the same amount of energy, for instance, as a very hot thing for a very short amount of time, like an accelerant placed on there. But only the latter is actually going to work. So we're going to talk about that time to ignition because that's kind of the easiest to think of intuitively, and we're going to look at that on a graph here. You'll notice the y-axis is just in terms of seconds. Specific gravity is the x-axis here, so you can kind of see where our oils are plotted out here, and that's from left to right: Santa Clara, Carpinteria, Sockeye, Santa Ynez, and Point Argeo. And here we have a range of about 5 to 40 seconds. So that kind of makes sense given that we have a decent range of specific gravity and we have a decent range of viscosity and other chemical properties. But we have a little bit of a correlation here. You can kind of see that as it gets a little bit heavier, you actually end up with, it takes a little bit longer. And it makes sense intuitively if you think of some of these oils as being very lightweight. They can, those lightweight hydrocarbons burn off quicker, ignite quicker. And then it's going to look at the same axes here, but we're looking at it weathered. And so that increases, it basically doubles the time, quadruples the time. And it looks pretty much like a pretty standard trend all the way across until you see the Point Argeo. And so we have this range that goes from basically 30 up to a minute and a half. It takes a little bit longer for weathered. And when it's weathered, it means that a lot of the light hydrocarbons are already gone. It's been sitting out for a while. And so all the stuff that ignites really easily, that's gone. So you have to wait longer for the heat to really get into that oil, to allow it to vaporize, for that M dot to leave the surface, and for those vapors to then ignite. And so that makes sense intuitively. The Point Argeo, we don't have a particular reason why that is that way. I'd love to discuss that with anyone who has some theories as to that. But what we can say is that was our heaviest and our most viscous. So it's a little bit harder for some of those vapors to leave when it's unweathered. And so there's not really that much difference after leaving it for a while. It didn't have all that much light hydrocarbons to lose. And so the weathering just didn't have as much of an effect. And we'll look at the same graph here, this time looking at it with some water. So we have our neat. So again, that's got no water in it. It's not weathered. And that's at the very bottom there. So that was that really short amount of time. And then we have the weathered, which is a little bit more. And then we have way up there, what happens if you add the 40% water. But this is the E40. So keep in mind, this is just if you take fresh and you emulsify it with 40% seawater. So we actually have this dramatic increase in time, up to 60 times more time to ignition, all the way up to 400 seconds, which makes sense because you basically have a lot of heat going into the water instead of the oil. And it takes time for either that emulsion to break down or for the water to start boiling while it's still in the emulsion. But you also notice again, now we have this Santa Clara on the left, where it actually doesn't have that much of a change. So this is important to know. You'll notice throughout that what type of oil we're using does matter. And one thing worth noting on this specifically because of the Santa Clara is that we think that there was a flow improver added to this from the pipeline. So we are getting a little bit of something else added to that may have also affected the emulsion stability. And so that same axis, but with the weathered samples. So here we can kind of see a better idea of what's going on, where again we have that weathered neat. So there's no water added to it. Then we have 20%, 40%, 60%. And as you go up, it's a pretty straightforward correlation there, where you have more water, takes longer to ignite. It kind of makes sense. It's harder to burn the water than it is to burn the oil. Up to 40 times increase, which is actually less than than what you had when you just added water. So that's worth noting, is that you can actually, if you have the weathering with you have a pretty significant shift in the time to ignition. But if you just added the water, you actually have a bigger shift. So that water content really dominates compared to just the weathering amount. And you'll see that, again, we have this kind of point on the far right, which is doing its own thing a little bit, and the sockeye in the middle, because the 40% and above actually would not ignite. So that's not a missing data. That's just data that of no ignition. And so that weathering, though, it does reduce the variability, which is worth noting. So we find that with the fresher oils, the neat ones, you'll end up with a little bit more uncertainty regarding the time to ignition. And then as you weather it, it's in a sense, it's a distillation process, but we're just saving the heavier parts instead of grabbing the light parts. And so those heavier parts are actually a little bit more easy to predict. So the weathering actually can be a benefit in the sense of tightening the error on these ignition models. And then now we'll look at the burn efficiency. And so this is very straightforward. We're not looking at combustion efficiency as in how clean it is. We're looking at how much was there versus how much we started with. And so the nice thing is, before, when we had the water, we could see exactly how much water we started with and how much we ended up with. So we could take care of that and account for that in our equation. And so we'll look through that. Again, this is just our neat. You can kind of see a little bit of a correlation, but nothing too strong here. But we have a max up there pushing 70%, and a low just over 50%. But then once you actually, and we want higher, right? We want more of this to be gone. But once you actually emulsify it, it drops down about 30%, 27% reduction in the burn efficiency. So that that makes sense, and that again you have the added water. And the nice thing kind of about this is that it was pretty much the same across the board. It was the burn efficiency went down in a predictable manner. Once you actually weathered it, you have a 14% reduction in the burn. So again, adding the water caused a greater reduction than simply weathering it. So here we have that reduction down to 14% less. And if you have this water and you have the oil sitting out, basically the water added is going to be the dominant factor. And then we have our weather trials kind of all at once right here. And you'll notice that in the middle there, we have again pushing 70%, which was nice, which is our Santa Clara on the left. And across the board is our need. But then we have this up to 80% with this 20% seawater. So in other words, adding that little bit of water actually improved our burn efficiency. And that takes into account having the water disappearing. And so that's kind of our biggest surprise for us. We were really happy to find this because it kind of means that the window of opportunity is opened up. We have a little bit more time perhaps to think about, oh, well, if we have a weathered oil sitting out there, but it's got a little bit of water in there, are we really out of luck? Or maybe we can actually get a little bit of benefit even though it's been sitting there in the waves for a little while. Now, of course, there's some limitations to all this. So the setup, of course, does not take into account flame spread, edge effects. We understand that. The no biological weathering on here. They're static emulsions. They're not mixed while we're burning. The mass loss was average, like I said, although we did later have a chance to compare that to the instantaneous data. And we do have oil reservoir changes, right? So taking into account that data that we plug into models, it's necessary to take into account that changes as the oil reservoir changes, or in the case of a lot of these Santa Barbara ones, maybe the oil reservoir is just no longer in production. But that doesn't change the actual setup itself. We actually really like the setup. We like the measurement method. It allowed us to show that oils that we thought were not ignitable previously are actually quite ignitable, and it gives us this chance to see that ISB can be a viable response even in a scenario with some added weathering. It's really good for seeing the relative differences between things, and it allows us to see these in a very small scale test, which was nice. And it opens up the idea of the window of opportunity and the water content being actually a benefit to ISB. And this is something that can, of course, be thought about and put into more research later. But that little bit of 20% water, that was our mile marker. Obviously, we'd like to look at that and maybe narrow that down to something a little bit more specific. And of course, we got to look at the burn behavior and the actual burn efficiency. We'd love to look more into, for instance, how the emulsions do break down, which has been talked about a little bit today. And then, for instance, chemical analysis and correlations with that. All the thanks to BSEE for their funding. As you noticed, they've had a big role out here, so we appreciate them and our investigators here. I'll be happy to take any questions here, or if anyone comes up with any questions later, you're welcome to contact me at this, and I can get them in touch with whoever or myself. And I'll hand it over to Ellen.
Thanks, CJ. Still exciting work. And again, the application to California is particular interest to us. Lindsay, do we have any questions for CJ?
Yes, there are a couple. So please let me know if you don't have time for all of them. From Paul Panetta, back on slide 10, is that the slick floating on the water, or is that in a pan?
On slide 10, is that mistaken?
Is that slick floating on water or in a pan?
Oh, it's in a pan. So the water is isolated from the oil, in other words. I know that most of the literature is actually putting oil on water, and we would like to do that with larger scale. It just introduces a whole lot of variability because you end up adding in mass that you can't account for because that water's in there. So this allowed us to separate that and allowed us to say, whatever mass we started with, whatever mass we ended with are known quantities. So that was actually separated, but the water is running underneath that. It's separated by a thin piece of stainless steel. It's running underneath that in a pool.
Great, we have a couple more questions. So this is a two-part question. Are there any plans to try burning the same oils, weathered and unweathered, using an accelerant to hasten injection or ignition? And are there any plans to try to burn these oils in Stevens burn torch?
Yes. So there's the answer is yes to both. With the accelerants, absolutely. We're actually in the process of putting together a large scale pan that will be able to look at this, and we'll be able to account for, as Paul asked before, able to account for oil on water. So we actually have a 3-meter pan. So that's something you can, you can lay down in it if you want to. It's huge, and part of that will involve actually putting accelerants on top of it, whatever accelerants we have available. Some of the one of the issues is that because of some of the platform shutdowns, et cetera, regarding the oil, we actually do run out of these specific types of oil. But there's no reason why we can't run these same methods with different types of oil, and we do have some in stock. The ones that have very stable emulsions, and the ones that are very kind of more viscous, like that Point Ardea before that we talked about, those are the ones that we've kind of put through that other burner as well, just for just kind of get an idea of our limits on that burner, and it can handle that. But we are trying to conserve our oil for the other tests for this as well. So it's an inventory problem more than anything else.
Those are all the questions we have.
Okay, great. Thanks again, CJ.
Yeah, fantastic. Thank you.